Supervised learning. Nearest neighbor methods are used extensively in predictive modeling. Sometimes they can be unsupervised, but often we have to do supervised machine learning. So we've seen that the k-nearest neighbor methods have many applications, recommender systems, imputing missing data. In fact, k-nearest neighbor graphs are sort of everywhere. We'll see that much of what happens in machine learning is based on k-nearest neighbor graphs, either directly or abstractly. So from the Scikit-learn documentation, here's what they say about nearest neighbor methods. Despite its simplicity, nearest neighbors has been successful in a large number of classification and regression problems. Unsupervised nearest neighbors is the foundation of many other learning methods, notably manifold learning and spectral clustering. You can find more information at this link, and we should note that k-nearest neighbors is not the only nearest neighbors algorithm. So unsupervised learning is where we infer hidden structure from unlabeled data. So if we had things were in classes 1 and class 0, then we would ignore that while we did the unsupervised learning. For example, suppose we wanted to cluster data into subsets. So for instance, we see some clusters in this image. And what do we mean by clusters? Well, we mean there's high similarity within a cluster, but between clusters there's low similarity. So we can see clusters here in this image where we have high similarity within these ovals, but low similarity between them. So we'll look at, in particular, spectral clustering, which is k-nearest neighbors combined with what are called eigenvector methods. Now, eigenvector methods come from linear algebra, and we're not going to do linear algebra, but the eigenvector methods are sort of intuitive in what they actually do in this application. So I don't think we'll miss them, the lack of linear algebra here. So let's suppose we had this data set and we connect it with k equals 3 k-nearest neighbors graph. Now the eigenvector methods are what allow us to know which edges we can remove in order to obtain high similarity within and low similarity between. That gives us a clustering of the graph, and then we can drop the graph and we have a clustering of the data. Now this looks like clusters are bunches, little pods of similarity structures. But similarity within being higher than similarity between doesn't necessarily give you little pods. So for instance, if we had this set of data and we wanted to cluster into two clusters, then here's our k-nearest neighbors graph with k equals 5. You can see there's obviously two clusters. One of the clusters, however, is sort of the subgraph that goes all the way around what's in the center. So there are our two clusters. Now spectral clustering is valuable. For instance, suppose we had this problem. It's clearly not linearly separable. But if there was some way we could pull apart into sub-regions, then it would be. Well, we can do that. Let's cluster. This is actually the same example we looked at on the previous slide. So we cluster into two clusters. And now we've got a clustering of our labeled data. So we did an unsupervised learning to get the clusters. Now we can go back to a classifier, but now we can apply the classifier on each cluster. And each cluster is linearly separable, as you can see. Now we haven't lost any information here. We also haven't really introduced any bias because we're just using a graph partition and applying to each partition. But we still have to worry about overfitting, and even though I say no bias, we did remove a few edges, so there is some possibility of bias. And there's other problems. We chose this distance similarity measure arbitrarily. Now for these examples it was just Euclidean distance, but later on we'll be using cosine similarity and other kinds of measures. The choice of k is often arbitrary, and that means that overfitting is always going to be an issue. And what about these graphs we produced? Well, K nearest neighbor graphs are rarely, quote, real world graphs. Complex networks in the real world tend to be scale free or small world, and they grow by adding edges much faster than they add vertices. Communities of communities of communities, so on and so forth. And they do this while maintaining a low average path length. So this is obviously not what we're thinking when we add edges. So this does not maintain low average path length. But something like this, where all the distances are less than or equal to 3, does. This is the kind of thing that we look for in the real world. But k-nearest neighbor graphs tend to be more like random graphs. So what is a random graph? Well, an Erdos-Renyi random graph has n vertices, and we're assuming n here is very large. And for any 2 vertices chosen at random, there's a probability p that they are adjacent. Each vertex is a Erdos-Renyi random graph that has about the same degree, just like k-nearest neighbor graphs, but not like scale-free graphs, where you have vertices with wildly different degrees. Most of them with small degree, but a few with very, very high degrees. But we have p equals k over n, which means the expected degree of a random graph is k. So if p is small, then the random graph tends to be disconnected with many components. If it's larger, then we get what's called an exponential graph, where the degrees are Poisson distributed for some large n. And we're working with k much less than n here. So we need supervised learning, and that means we often use a feature or class labels to train, validate, and test an application. So when we do supervised learning, that means we get the ability to successively refine and improve based on whatever we're using for the labels. It creates confidence in the use of the algorithm. And we can use k-nearest neighbors via training, validation, and testing to reduce statistical bias. So for instance, maybe a means of choosing a better choice of k, among other things. And also statistical bias, for example, when we do imputation. Now, if an algorithm predicts an average of a of x for variable x, then rigorously, statistical bias is the difference between the average and the actual theoretical expected value. Just reminding us that statistical bias is not a holistic term. It actually can be defined very precisely. So the supervised learning scenario, for instance, in recommender systems and imputation, what we do is we require a training set of known data that's used to predict values for a test set of data whose value for a certain feature is not known. So if we're imputing, the test set is the ones that have missing values. In the recommender systems, the test set are the ones we want to make predictions for. And when we use supervised learning, we're informing or teaching or training an algorithm using a training set whose features and class or labels are known. And then we predict the unknowns for the separate testing set. Now we actually tend to divide the training set also. As a matter of fact, we're just giving you the simplest version of this whole supervised learning concept. So the training set informs or teaches the classifier, and the validation set assesses the classifier. And so a lot of times we'll actually take a sample from the training set as a validation set that we can use to successively refine and improve before we actually do our testing. So let's look at an example. So the Titanic challenge is where we're trying to predict if a given passenger survived the sinking of the Titanic. It's a popular ongoing introductory competition that Kaggle uses to recruit participants to this machine learning challenge. We'll actually be looking at the Titanic challenge fairly often in this course. Now Kaggle knows if a passenger survived, and thus they can evaluate those who participate. And so we start with the passenger data that they provide. So the data set is 12 features of 1,309 passengers that on the Titanic when it sank. The training data is 891 passengers known to have either survived or not. The test data is the remaining 418, and their survival status is not given. And so we use the training data to try to predict which of the 418 survived, and that's the challenge. Now, missing data. Before we can do any predictions, we need to impute missing ages. Not all of the ages were recorded for the passengers. So we could do one of three simple approaches. We could replace all the missing ages with the average over the entire data set. Now, that's going to be biased. There's probably a lot more children than there are senior citizens, and people tended to be, passengers on the ship and the crew. So maybe we use the median, or maybe we create a simple social network model. So what we can do here, I've got the notebook, and you'll see when you get there that we have the data and the age data. We have missing values. So here's the features that I talked about. There's a description of the features. We can describe the Titanic data, look at the averages. You'll notice the ages, there's only 1,046 ages. There's a lot of missing data, a lot of missing ages, and we're going to have to impute those. So for example, let's look at passengers 300 to 304, and you'll notice that their ages are missing, but they have certain features. Maybe we can use those features. So notice what I'm doing right now is I'm actually filling all the missing ages with -1, and that way I can figure out what my test set's going to be. So I'm going to regroup by all those that have the -1. The remaining is going to be the training data, but then we're going to split off from the training data a validation set. So the test data we'll apply this to later. The validation data is what we're going to use to refine, and the training data is what we're using to actually make predictions. So notice if we impute the mean, everybody is predicted to have an age of 29.7. Well, when we apply that to our validation set, we get a mean that should be 0 for the differences, and we don't get a nice distribution. Let's try the median. So now we're going to look at predict age as being the median. The median age is 28. And what does that mean? That means everybody is assumed to have a mean of 28. So I'm taking the differences here, and we should get 0 on average. We didn't. We got 3. So now what we can do is we can start defining some subclasses or some programs that uses information, for instance, passenger class. And now we can do a k-nearest neighbor network and use neighbors to impute ages. And this is a very simple first approach. Notice again we're going to look at the difference between the actual age and the predicted. And notice that there's a lot of similarity, a lot more similarity in ages than just everybody being the same age. There's also a little nicer shape to the distribution, looking a little more like a bell curve. And we're a little closer than we were. Now in the notebook, we actually have a very nice method that gets the mean down to almost 0 and greatly reduces the standard deviation using this social network model. So in summary, supervised learning. We partition training data, into training data. Class is known. We teach the classifier how to make good class predictions. Validation, the class is known. We assess and improve the classifier, and the test data, the class is not known, And our ultimate goal is to develop an algorithm that can predict the class of an observation in the testing data where it's unknown. Well, and it doesn't always have to be a class, it could be a feature where, for instance, we have missing values. So the key is classifiers are going to have to learn how to make good predictions. And their learning tends to require close supervision.